Assalamualaikum warahmatullahi wabarakatuh. Today I want to teach you the autoregressive or AR model in time series. Now the autoregressive model in time series, it takes a simple linear regression model that involves the dependent variable and the independent variable. So if you refer to the time series model, these are refer to regression models. Right? These are regression model. Okay? Now, if you refer to the regression model, this is a regression model. So the regression model say that this is refer to regression model. Okay? This is refer to regression model. Okay, now this is refer to regression model. Okay? Now this is a regression model. So now for the regression model, we have yi is equal to beta naught plus by beta 1 xi plus by epsilon I. So what I mentioned just now is refer to linear regression model, but in AR model, uh, we have AR1. Okay, we have AR1. So AR1 is equal to yi beta naught plus by beta 1 y I minus 1 plus by epsilon I. Because of for the AR1 model, we refer to we regress between yi and the previous data. Okay, yi and the previous data. Let's say I have the data here. So let's say here is my t time, okay, time, and here is my yi, okay, yi. So I have here, okay, let's see my time here is 1, 2, 3, and 4. So this is a y1. This is a y1. Let's say here is y1, and here is y2, y3, and so on and so forth. So let's here is let's say this is let's say I have here 2, 3, 4, and 5. So meaning to say for the regression for the AR model, we regress this data yi between yi and the data to the previous one. So for this case, this is yi and yi minus 1, okay, is equal to, here is we regress, so if here is yi and your yi minus 1 is this part is equal to 4, and here is 3, and this is 2. So we just concentrate on this data. So meaning to say, now your data here is your yi is equal to, instead of we start with 2, we start with 3. So we have 4 and 5. And then your yi minus 1 is 2, 3, and 4. Okay. This is for the what you call the ER1 model. Now, so basically for the regression model, we have like this. Let's say I have here, I have this my y, and this my x. So the simple regression model think that taking that this model is y is equal to beta naught plus by beta 1 plus by multiply by s sub 1 s sub I and plus by epsilon I yi. Okay. And this part, this thing is the beta naught or the value of y when x is equal to 0, and the slope here, these are the gradient, and this gradient is equal to beta 1. Gradient is equal to beta 1. So the same thing applied to regression model. So for the regression model, we have here, let's say, for the regression model AR1 or AR1. So I have here this my yi, and instead of x here, we have this one is a yi minus 1. This is a regression model. So that's why our regression model here become beta naught, or in regression, we want to differentiate between regression and autoregressive. So we just put here y sub I is equal to 5 naught plus by 5 1 y I minus 1 plus by epsilon I. This for AR1 model. And then for the AR2 model, so for AR2 model, let's say I want to find AR2. So AR2 is equal to 5 naught. Instead of beta naught, I use 5 naught plus by 5 1 y I minus 1 plus by 5 2 y I minus 2 plus by epsilon I. This involves two variables here, y1 and y2. This becomes multiple regression. So this is a linear regression. This is a linear regression because we have one variable here. So here this is a linear, and this is a multiple regression. And then for AR3, for example, so if you want to find AR3, autoregressive lag tree or third order. So these are first order. This is known as the first order, and this is known as the second order. And the third order autoregressive, or the third order model is AR3. So y sub I is equal to 5 naught plus by 5 sub 1 y I minus 1 plus by 5 sub 2 y I minus 2 plus by 5 sub 3 y I minus 3 plus by epsilon I. These are AR3 model. These are AR1 and these are AR2. Okay. Then we go to the next slide. This what I call the what I mentioned just now is this is a AR1 model. So this is the AR1 model. Okay. AR1 model. AR1 model. So y sub I is equal to 5 naught plus by 5 sub 1 y sub I minus 1 plus by epsilon I. This is AR1. So this error, the error term here, or white noise here, is a white noise. So white noise, or the error. Now the error here, in regression we say the white noise, but this is the error here. The error here is normally distributed the mean 0 and variance sigma. And covariance for epsilon I is equal to 0, and covariance for epsilon I and yg is also equal to 0. These are the basic properties here. These are assumption here. These are assumption. So the assumption say that the assumption for regression PR model is, so epsilon I is normally distributed with mean 0 and variance sigma squared, variance sigma, and the covariance between epsilon I and epsilon j is equal to 0, and the covariance between epsilon I and yj is equal to also equal to 0. These are the first order or AR1 model. Now, the same thing apply to AR2 model. So, AR2 model, yeah. So this y sub I is equal to 50 plus by 51 yi sub I minus 1, 52 yi minus 2 plus by epsilon I. These are AR2 model. And then if you want to find AR3, what I mentioned just now is yi. So for AR3 model, so the third order AR3, so AR3 is y sub I equal to 5 sub O plus by 5 sub 1 yi minus 1 plus by 5 sub 2 yi minus 2 plus by 5 sub 3 yi minus 3 plus by epsilon I. It depends on the order here. So if you have the third order, you just put yi minus 3 here. Okay, now let's say I want to find the p order, ARP order. P order autoregression process is y sub I plus by 5 naught plus by 5 1 I minus 1, 5 2 I minus 2, 5 3 I minus 3, dot until 5p, because of we have p order here. 5p I minus p plus by the term here, or the white noise. This is how we write the autoregressive model depending on the order. Right? So we have first, second, third, fourth, fifth, and up to p order. So this is how you write the regression or autoregressive model for the time series. Now, let's say, so the next part is the property of the time series, the AR model. The properties here. For property number 1, okay, property number 1, the mean for yi, the mean for 1i, okay, the mean for yi for the ARP process or ARP model is mu. The mean here is mu is equal to 5 naught divided by 1 minus by summation of from j from 1 to p 5j. And then property number 2, this is talking about, this is a ARP model. Yes, ARP model. Okay, yeah, this is a ARP model. Let's say I want to find the mean for the second order. So let's say I want to find AR2, the mean for AR2, the mean for AR2. So the mean for AR2, the mean for AR2 model, mu is equal to 5 naught over 1 minus by 5 1 plus by 5 2. This is the what you call the mean for AR2 model. Now the mean for AR3 model, the mean for AR3 model is equal to 5 naught over 1 minus by 5 1 plus by 5 2 plus by 5 3. Now the mean for AR4 model, for example, AR4 model, the mean here, the mean for AR4 model is equal to 5 naught over 1 minus by 5 1 plus by 5 2 plus by 5 3 plus by 5 4. These are how we get the mean for here. 1 2 3 and 4. And in common, in general, mean for ERP model is 50 over 1 minus by summation of 5j. J is from 1 to p. Okay. Now, property number 2, this will be talking about for the AR1 model only. Okay. AR1 model only. So the variance for AR1 model is equal to sigma square over 1 minus by 5 1 square. And then property number 3, so the autocorrelation for, or the correlation of ER1 model is rho h equal to 5 1 h. Rho h is equal to 5 1 h. This is the correlation or the autocorrelation of ER1 model. Now I want to prove here, to prove mu is equal to, and so we have three property here. So every and each property here, I want to prove for every and each property here. So I want to prove for property number 1, property number 2, and property number 3. Now we start with property number 1. So we start with property number 1. So how to prove here? Okay, now so I want to prove the property number 1. So now, saying that for the mu is equal to 5 naught over 1 minus by summation of j from 1 to p 5j. So I want to prove the mean for ARP model is this one. This is the mean for ARP model. So the mean for ARP model here. So we know that, so because of, we want to find the mean of ARP model. So by definition, mean is the expectation of, if you have the ARP, y is equal to, so the model for ARP, so model for ARP, so ARP, ARP is equal to, or implies y I is equal to 5 naught plus by 5 1 y I minus 1 plus by 5 2 y I minus 2 plus by 5 3 y I minus 3 plus by dot plus by 5 p y I minus p plus by epsilon I. These are ARP model. Now I want to show you, I want to prove that the mean for this ARP model is equal to 5 naught over 1 minus by sigma 5j. Okay, I want to prove this one. Okay. So to prove this one, we use this equation here, the ARP model. The ARP model is written as this. It's the same thing here. It's equal like this. Same thing here. So I want to prove the mean here. So to find the mean here, by definition, mean is the expectation of yi. Expectation of yi is equal to the mean. So mean to say you need to find the expectation for all the function here. So we just put here. So here become expectation of yi, and the mean is equal to expectation of your yi is 5 0 plus by 5 1 yi minus 1 plus by 5 2 yi minus 2 plus by 5 3 plus by 5 4 and so on and so forth. And just put this plus by dot plus by phi p yi minus p plus by epsilon I. So we need to find the mean here, the expectation of value of this one. Okay. So for this case, so you can expand this equation here. You can expand the thing here become. So if you expand here, the thing here become the expectation of yi here. The expectation of yi mean, okay, mean or the expectation of yi is equal to expectation of phi 0 plus by the expectation of phi 1 yi minus 1 plus by the expectation of phi 2 yi minus 2 plus by plus by the expectation of 5 sub p yi minus p plus by the expectation of epsilon I, or ei, the expectation of ei. Now, expectation of a constant is a constant. So we assume that this is a constant. Yeah? It's a constant here. The expectation of a constant is a constant. So you can write like this. So here this become 50 plus by. So because of here 1 here is a coefficient, we just put here 1 expectation of yi minus 1 plus by 2 expectation of yi minus 2 plus by plus by 5p expectation of yi minus p plus by expectation of epsilon I. Now, by definition, the expectation of yi, expectation of yi equal to expectation of yi minus 1 equal to expectation of yi minus 2 and so on and so forth, because of there are this is the definition by definition. This is by definition. So expectation of yi equal to expectation of yi minus 1 expectation. So if I put here as a mu here, expectation of yi is equal to mu, then I can what you call, I can substitute here. So here become, so expectation of yi, expectation of mu, expectation of yi equal to mu is equal to, so expectation of phi 1 just now is equal to phi 0 is equal to phi 0 plus by phi 1 ey sub I minus 1 is equal to mu plus by phi 2 yi minus 2 also mu plus by plus by 5 sub p yi expectation of yi minus p is equal to mu. Then the expectation of ei, the expectation of the white noise is equal to 0 plus by 0. Okay, by definition, the expectation of epsilon I is equal to 0. Okay, so here we have mu. In other words, expectation of yi is equal to mu. Mu is equal to phi 0, phi 1. So we can simplify this as a 5 sub 0 plus by mu 5 sub 1 plus by 5 sub 2 plus by plus by 5 sub p plus by 0. Okay. So so this can be written in the form of, so if I put here, I just bring this thing to the left here. So mu minus by mu 1 plus by 5 sub 2 plus by up to 5 sub p is equal to 50. because of I bring this thing to the left, so I got mu minus by this thing. Now here this can be written as so mu 1 minus by 5 sub 1 plus by 5 sub 2 plus by plus by 5 sub p is equal to 5, 0. Okay. So this is how we prove the thing here. Okay. So this can be written as, this thing can be written as, this can be written as, I just put here, this thing can be written as. So in other words, your mu here is equal to 5 sub O over this thing, the multiplication here, if you bring to the left, become division. So y minus by 1 minus by 5 sub O plus by 5 sub 1 plus by plus by 5 sub p. Okay. So so here mu is equal to, so this thing, so this refer to this one. Okay. 0. And here is 1. Okay. And this thing can be written as summation. This means summation. Okay? So this thing is a summation of j from 1. Sorry, here is 1. Here is 1 sub 1, sub 1, sub 2, so on, so on. So this refer to j from 1 to p. So summation. This is a summation. Okay? This if you add here means you just put a symbol of summation from 1 to p. So this is how we prove mu is equal to 50 over 1 minus by summation of j minus 1 p 5 sub j. These are for ARP model. The mean for ARP model is this one. So this is how we prove the mean for ARP model is 5 sub O 1 minus by j minus by 1 j equal to 1 to p 5 sub j. These are the proof for ARP model. Okay, next is okay, these are how you prove here. So we just put like this. How you prove here again. So, okay. Now, next one, I want to prove the variance for AR1 model. The variance for AR1 model is given by sigma squared over 1 minus by 5 1 square. So the variance for AR1. Now, by definition, if we take the concept of let's see, we take the concept of mean 0 here. So the expectation of yi, the variance of yi, by definition, for the time series AR1 model. This one AR1 model, refer to AR1 model. The expectation, I want to find the variance of yi, the variance for variance of yi. So I want to prove the variance is equal to this one. So variance of yi is equal to the expectation of yi and yi. This is a variance of yi by definition. This is by definition. So we know that for the AR1 model, AR1, the yi is equal to 5 naught plus by 5 1 yi minus 1 plus by epsilon I. These are the first what we call the AR1 model. So now this variance of yi can be written as expectation of, so yi is 5 naught plus by 5 1 yi minus 1 plus by epsilon I is yi multiplied by yi is 5 naught plus by 5 1 yi minus 1 plus by yi. So yi minus 1 plus by epsilon I. So we try to this is referred to yi, and here is also referred to yi. Because of the variance of yi is equal to expectation of yi multiplied by y. And since this is the AR1 model, so your yi is 50 plus by 51 yi minus 1 plus by epsilon I. And then the other yi is also 50 plus by 51 yi minus 1 plus by epsilon I. So if we expand this equation here, so here become the expectation of so 50 multiplied by 50 is 50 square plus by 50 multiplied by 51 y1 is 5 not 51 yi minus 1 plus by 50 multiplied by epsilon I is 50 epsilon I. Then you expand again, you expand still expand. 51 yi minus 1 multiplied by 50 is 50 51 yi minus 1. Then this one multiplied by this one is plus by 51 square yi minus 1 minus by yi minus 1. Then this thing multiplied by epsilon I, we have 51 epsilon 51 yi minus 1 epsilon I. Okay, then the third expansion here is epsilon I multiplied by 50. So you have epsilon I 50 plus by then epsilon I 51 yi minus 1. Then epsilon I multiplied by epsilon I is plus by epsilon I. Okay, these are how you expand the thing here. So now if we can see here we have a two common factor here, two things here. This thing is the same as this one, and this one is the same thing, isn't it? Now the other one is epsilon I, epsilon I, epsilon I 51. We have here epsilon. Okay, so here yi1 is an epsilon I. Okay, this thing, this one and this one is the same thing, eh? And the rest is a standalone here. So here ei1. Okay, this thing, and this thing also the same thing here. Okay, the rest is okay. So now you can rewrite the thing here. Okay, you can put as a so now I can write here like this. So this become the thing here become so here is equal to this part is equal to expectation of 5 naught square plus by this thing and this one, okay, this one and this one, same thing. So I put 2 5 naught 5 1 y I minus 1 I minus 1, and then I have here the same value here, this one and this one. So you can write like this 2 5 1 epsilon I y I minus 1. Okay, there. Now, then we have again we have this one, this one, this one, and this one. 2 plus by 2, 5, 0, epsilon I. Okay. Then we just rewrite the other part here. We had the equation here become plus by then plus by 5 1 square yi minus 1 yi minus 1 and plus by 1 then plus by the last one is plus by, don't forget to plus by epsilon I and epsilon I. Okay. These are here, okay, the, the expansion of these two equations, yi and yi. So just right here. So now you have expectation of 50 squared plus by 2 50. This is a 5 1, isn't it? This is a 5 1. This is a 5 1. Okay. 50 5 1 y I sub 1 plus by 2 5 1 epsilon I. These are 2 y I minus 1 plus by 2 sub o epsilon I plus by 5 1 square y I minus 1 y I minus 1 plus by epsilon I. Okay, so I cancel off this one, so just clean here first. Okay, so I'll try to rewrite again. So the final part here, what we have just now, the variance of y just now, the variance of y I is equal to the expectation of, we expand just now, we have 5 sub o square plus by 2 5 sub o 5 sub 1 yi minus 1 plus by 2 5 sub 1 epsilon I y I minus 1 plus by 2 5 sub o epsilon I plus by 5 1 square y I minus 1 y I minus 1 plus by epsilon I square. Okay. Now, if I expand, I just throw away the bracket here, so this can be written as, expectation of 5 naught 5 sub o 5 sub o, so 5 sub o square, or expectation of 5 sub o 5 sub o means 5 sub o square plus by, because of 50 5 1. So the thing here, 50 and 51 is a constant here. 50 and 51 is a constant. 50 and 51 is a constant. So we just put here 2 Let's put here to support you can put here to 5 support 5 sub 1 expectation of yi minus 1, okay, and then plus by okay, plus by 2 5 1 is a constant multiplied by expectation of ei y I sub 1 plus by 2 is constant here, 250 is constant expectation of epsilon I plus by, so 5 sub 1 is a constant multiply expectation of y sub I minus 1 y sub I minus 1 plus by expectation of epsilon I square epsilon I, or in the way we put epsilon I and epsilon I. Epsilon I square means epsilon I and epsilon I. Epsilon I and epsilon I and epsilon I. Okay, now by definition, so expectation of 50 and 50 is a variance of, if you have two variables here, the same variable here, expectation of the two same variable here is equal to the variance of sub 5 sub 0. And these are constant. The variance of constant is so now we before that we can write this one as a, so here become the thing here become, so variance for 5 sub 0 plus by 2 sub 0 sub 1. Now here is expectation of y I sub 1 minus 1 plus by 2 5 1. Now if you have the same variable here, ei and ei means you have a variance, but if you have ei and yi minus 1, the two different variables here, this is known as covariance. So if you have different variables, we say that we have a covariance here. So I have a covariance here, covariance ei yi minus 1, ei y minus 1, and then we have 250 expectation of epsilon I plus by 2 5 sub 4 expectation of epsilon sub I, then plus by 5 1 square. Now if we have two variables here, two same variables, here is y sub 1 and y sub 1, so the two variable means we have a variance y minus 1, and then now if you have two variables here, the same variable here, expectation of exi is a variance of exi, variance of e sub I. So these are how we write the term here. Now this can be written as, so I just cancel off this one. Okay. So many things here. I cancel all this one, all these things. Try to cancel all these things. Try to cancel all these things. Okay. Now, here is this. You go back here. Here is the variance of variance of yi. Of yi. This is for AR1 model. Okay. Now this can be written off. Now by definition, if you have a constant, this is a constant, this is a constant, y phi sub o is a constant. A variance of a constant, by definition, a variance of constant is zero. Constant is zero. Plus by 2 sub o sub 1 expectation of yi. So just put expectation of yi. I do not know what is the expectation of yi minus 1 plus by 2, 5, 1. Now the covariance of two different variables here, if you have the because of they are independent here, the covariance here becomes 0. So if you have two different variables here, ei and e, the covariance here becomes 0 multiplied by 0. And then here y sub 2 sub o, 2 plus by 2 sub o, 2 sub o, the expectation of epsilon I. Epsilon I, by definition, epsilon I, ei or epsilon I is normally distributed with mean 0 and variance sigma square. Variance sigma square. Now, so the E here, the expectation of epsilon I or the mean of epsilon I is equal to 0, so multiplied by 0 here. 0. This is the expectation of EI. This is the variance of EI. Now, so variance of yi minus 1, okay, so then plus by so we have 5 sub 1 square, so just put variance of yi minus 1, we do not know what is variance of yi minus 1, plus by, now the variance of epsilon I is equal to, by definition, the variance of epsilon I is sigma square. So variance is equal to sigma square by definition. So this is a variance of yi. So variance of yi, variance of yi. So the 0 here you can put off here, 0 here you can put off. So I have here. Now, because of we consider this is a zero mean, the concept of zero mean, the variance here is also equal to 0. Okay? The variance is equal to 0. And sorry, the mean here is equal to expectation of yi minus 1 is also equal to 0. Because we assume that we consider this the concept of time mean 0 time series. So the mean here is equal to 0. Okay? We consider a mean equal to 0. So this part is also equal to 0. Okay? So the thing here we have variance of Vyi equal to 5 1 square multiplied by V multiplied by variance Vi minus 1 plus by sigma square. Okay, this is the final answer. So, but now we know that by definition, the variance of yi1, variance of yi1 equal to variance of yi, variance of yi. Okay. So for this case, so variance of yi is equal to 5 sub 1 square. This is a variance of also yi plus by sigma square. So if you solve this one, you will get, if you solve this one, you will get, so variance of yi minus by 5 sub 1 squared variance of yi equal to sigma square. So, so this can be written as variance of y sub I multiply 1 minus by 5 sub 1 square equal to sigma square. That's why we get variance of yi equal to sigma square over 1 minus by 5 1 square. It is a one answer. It's a one answer for we try to this is a proof. This is how we prove the variance of yi is equal to sigma squared over 1 minus by 5 1 square. It is the third property of ER1 model. ER model. So we have proved ERP, mean for ERP, and we have also proved the variance for AR1. So mean for ARP and the variance for AR1. Variance for AR1 is equal to sigma square over 1 minus by 5 1 square. Now the next part I want to prove the third property. The third property here is referred to the proof for the second property here. Okay, proof for okay. So now I want to prove the third property. So the third property say that the correlation of for AR1 P sub H is equal to 5 1 raised H, and these are the lag H or the lag K. You can put lag K or lag H. Okay, lag K or lag H. PH equal to 5 1 5 1 raised H. Okay, now the concept of covariance. Now I want to find the covariance. Okay, so I want to find the covariance. Here I want to prove this one. I want to prove this one. I want to prove this one. Okay. So we have to understand that covariance of yj and yj is an expectation of yj and yj, and this thing is also this is also we assume that this is zero mean. Okay, zero mean, property on zero mean, so yj is equal to yj. Variance this is a variance of variance of yi is equal to covariance of yi yj, and covariance of yi yj is a yi yj. Okay, this is how we prove that. Okay, now so let's say I want to show that the lambda gamma sub k. So gamma sub k is referred to the covariance. Okay, this this thing is a variance. This thing is a correlation, autocorrelation. It's a autocorrelation. It's a autocorrelation or the correlation. Rho here is a autocorrelation. So I want to prove this one. Rho k is equal to phi 1 is k, and the other one is the this part. This is a autocovariance. This is a autocovariance. For covariance, for the time series, we say that we put a term of autocovariance. In other words, it's covariance. It's an autocovariance. This is autocovariance. Autocovariance. Or in the general form, or in the normal form, normal terms, if we say that covariance. Covariance in time series, we say that the autocovariance. Now, autocovariance or lambda sub k is a gamma sub k. Gamma sub k is equal to is a covariance between yi and yi minus k. So I want to prove this one. So to prove this one, this is equal to lambda 1 raised k lambda 0. So to prove this one, just for by definition, covariance of yi minus k is equal to expectation of yi and yi minus k. So we know that by definition, this is a AR1 model. Okay? AR1. This is a AR1 model. Okay? Now, for the AR1 model, expectation of the yi here, y sub I is equal to, so because of we assume that this is a zero mean time series, we don't have to put 5 0, which start with phi 1 yi sub 1 minus 1 plus by epsilon I. We do not put phi 0 because of we assume that the graph here, we start from 0 here. Okay? This is y is equal to, there's no phi 0, we start with phi 1, because of phi 0 is equal to 0 here. Here is phi 0 is equal to 0, so phi 1 y sub I minus 1 plus by epsilon I. This is yi. Here is yi minus 1, and here is your yi. This is the thing like this. Okay? The proof is for this one, this function. Okay? So our mean here, the concept of mean here is the concept of here is a mean 0. Okay? So y sub I is equal to phi 1 y sub I minus 1 plus by epsilon I. Okay? Now, so to prove here, you substitute for all, you substitute yi here equal to phi 1 y minus 1 plus into this equation, to this expectation value here. Okay? So I just put like this. Okay? Again, okay, my covariance here. So the covariance, so gamma sub k is gamma sub k is equal to the covariance between y sub I and y minus k, and this is equal to expectation of y sub I minus k. Okay. Now, like what I just said just now, this is this is equal to expectation of. So your yi is equal to 5 1 yi minus 1 plus by epsilon I, isn't it? Then multiplied by yi minus k. Okay, yi minus k. Okay. So we try to expand this one. So if we expand this one, we will have expectation of if you expand this one, we get expectation of 5 sub 1 yi minus 1 multiplied by yi minus k plus by epsilon I yi minus k. And then if you open the bracket here, so I have here become this thing become expectation of 5 sub 1 yi minus 1 yi minus k, so plus by the expectation of epsilon I yi minus k. Okay. Now this can be written as now here can be written as 5 sub 1 epsilon yi minus 1 yi minus k plus by expectation of expectation of ei and yi minus k is the covariance epsilon I and yi minus k. And this covariance, because of they have different variables here, the covariance here, because of they are independent, the covariance here becomes 0. This thing becomes 0. This whole thing here, the whole chunk here, the whole thing here, covariance of two different variables by definition is equal to 0 here. So that's why we have the final answer here is equal to 5 sub 1 expectation of y I1 y I minus k. Okay, this is the final answer here. And this can be simplified as, because of by definition, this thing, expectation of y I minus 1 y I minus k, this thing is equal to the expectation of the covariance here is equal to lambda gamma. The covariance here is a gamma sub k. The covariance here is a gamma sub k minus 1, because of you have k here minus, so it's here is minus 1 here, k and minus 1 here is, this is the by definition, expectation of yi minus yi and yi minus k, in other words, is covariance is a gamma is equal to gamma k minus 1. There is a proof here. There is a one proof here. So I do not want to prove here. So because of so many proof, so we just memorize here. Y is expectation of yi minus 1 yi minus k. In other words, a covariance between I minus 1 and I minus k is a gamma k minus 1. So we just put here, because of here we have expectation of yi minus 1. So here you can put 5 sub 1 gamma k minus 1 with the final answer. And now, also by definition, gamma k, by definition, gamma k is equal to, by definition, this also by, there is a proof here also, gamma sub k is equal to 5 1 raised k 5 0, 5 lambda 0, gamma 0. Gamma 0 is a means for, is a variance of yi. Gamma 0 is a variance of gamma 0 is variance, gamma 0 is a variance of yi. So gamma k is equal to variance of k is a 5 1 raised k. This also, there is a proof here. So we just memorize this one. Gamma k is equal to gamma 1 raised k gamma 0. So the thing here, so here is your, this is a gamma k. So gamma k, so now gamma k is 5 1 k 5 0. Actually lambda gamma k is equal to 5 1 raised k gamma 0. So if I have k minus 1 here, k minus 1 here. So if I have k minus 1 here, so gamma k is 5, 1. So gamma k minus 1 is gamma. So here becomes 5. So if gamma k, I have 5, 1 raised k. So if I have gamma 1 here, it's become 5, 1. Gamma k minus 1 is 5, 1. So here is k minus 1, 5, gamma 0. These are gamma k. So if I solve this one, we get 5, 1 multiplied by 5, 1 raised 1 multiplied by 5, 1. K minus 1 is there. Also go back to 1 minus 1 is 0. K 5, 0 plus k, or 5, 0 plus 5, 1, 0 plus k, or 5, 1 raised k gamma 0. This is how we prove the third properties here. So gamma k is equal to gamma 1k gamma 0. Okay, this is how you prove the third properties of what I call the covariance here. The covariance of k. The covariance of k is equal to gamma 5, 1 raised k 5, 0. So these are the covariance for k. Okay? So these are proof for AR1. AR1 for the AR1 model. AR1 model. So these are really with AR1 model. Now the next part is I want to show you. Okay. So see we have gamma k. Gamma k is equal to, we have proof gamma k is equal to 5, 1 raised k gamma 0. Okay. So then I want to show you this one. The final one is the correlation here. The correlation here. So by definition, the correlation of rho sub k. Now the rho sub k, I want to prove that rho sub k is equal to gamma k over rho sub k is equal to 5, 1 raised k. So we want to prove the final one. We want to prove this for AR1 model. So rho sub k, I want to show you the rho sub k here. Rho sub k equal to this thing. So rho sub k. So I have rho sub k is equal to 5, 1 raised k. So I want to prove this one. Rho sub k is equal. So by definition, gamma k, rho k, rho RHO. This is a phi. Phi, 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 and rho is rho. So rho k is equal to 5, 1 raised k. So by definition, rho k is equal to gamma k over gamma 0. And we know that gamma k, we have proved just now, gamma k is equal to 5 sub 1 raised k gamma 0 divided by gamma 0. So the final answer here is equal to gamma 5 sub 1 raised k. These are how you prove the autocorrelation. This is known as an autocorrelation. Just now is the previous one is so gamma k is the auto covariance. And I have proved the property 1, property 2, and property 3. This is regarding to the proof for auto correlation. This is a proof for variance, and this is a proof for the mean. Okay, the mean. This for ARK, and here is a proof for AR1, and this is a proof for AR, also AR1. So the rest is R2 and so on. What is quite tedious, it's quite complicated to prove. We just prove these three things. Yeah. So if any question regarding to this type of lecture or this type of notes, so the thing here is you need to you are just if you are I ask you to prove the mean, variance, and autocorrelation for ARK, AR1 model. Okay? So I think that's all for today. Okay? That's all for today. Until then, so so next week I will teach you still on AR model. Then week after next we can go to MA model and AR MA model, ARMA model. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh.